What specific problem does AnchorAttention aim to solve regarding the challenges of long context training in LLMs?
AnchorAttention aims to solve the problem of inconsistencies in positional encoding that arise when using BFloat16 precision during long context training in LLMs. Specifically, it addresses the breakdown of Rotary Position Embedding (RoPE's) relative positional encoding properties, which is exacerbated by the accumulation of numerical errors as the context length increases. By introducing a shared anchor token that maintains a consistent position ID across all documents, AnchorAttention eliminates the discrepancies caused by treating the first token differently in various windows. This design allows the model to learn the full spectrum of rotational angles without requiring sequences to reach the maximum context length, thus improving long context performance while reducing the computational burden. Overall, AnchorAttention enhances the model's ability to handle long contexts effectively while minimizing the precision issues associated with BFloat16.
How does the proposed AnchorAttention method work? Illustrate its functioning step by step, particularly focusing on how it addresses the issues with BFloat16 and RoPE.
The proposed AnchorAttention method functions by introducing a shared anchor token, designated as the beginning of sequence token, less than boss greater than, which is assigned a fixed position ID visible to all documents within the context window. This design addresses the discrepancies in RoPE's relative positional encoding caused by BFloat16 precision, particularly the significant contribution of the first token to these deviations. By treating the first token as a common anchor, AnchorAttention eliminates inconsistencies in positional understanding across different documents, allowing the model to maintain a consistent relationship between the beginning of each document and the starting position ID. Additionally, this method reduces the number of tokens involved in attention computations, preventing the accumulation of numerical errors that arise from attending to all previous tokens. Consequently, AnchorAttention enables the model to learn the full spectrum of rotational angles even when processing sequences shorter than the maximum context length, thus enhancing long context training efficiency while mitigating the precision issues associated with BFloat16.
Can you provide a simple example that demonstrates how AnchorAttention processes a sequence of tokens, particularly regarding its handling of the shared anchor token and positional IDs?
AnchorAttention processes a sequence of tokens by designating the first token, typically the beginning of sequence token less than boss greater than, as a shared anchor visible to all documents within the context window. For instance, if we have a sequence of tokens from multiple documents, instead of assigning different position IDs to the first token of each document, AnchorAttention assigns the same position ID to the less than boss greater than token across all documents. This ensures that the model maintains a consistent understanding of the positional relationship, as the first token is always treated as the starting point. Consequently, subsequent tokens can retain their relative positional encoding properties without confusion, as they are assigned continuous position IDs from the start to the end of the window length. This approach allows the model to learn the full spectrum of rotational angles effectively, even when processing sequences shorter than the maximum context length.
What are the theoretical or practical benefits of using AnchorAttention compared to previous methods such as standard intra-document attention and full attention in terms of long context performance?
AnchorAttention offers several theoretical and practical benefits over standard intra-document attention and full attention for long context performance. Firstly, it addresses the inconsistency in positional encoding caused by the first token's relative positional properties, which is a significant issue in previous methods. By designating a shared anchor token, AnchorAttention ensures that all documents within the context window reference the same starting position ID, thus maintaining positional coherence. Secondly, it reduces the number of tokens involved in attention computations, which mitigates the accumulation of numerical errors that arise with longer sequences, a problem exacerbated in full attention. Empirical results demonstrate that AnchorAttention consistently outperforms both standard intra-document attention and full attention on long context benchmarks like Ruler, indicating its superior capability in handling extended contexts. Additionally, it allows the model to learn the full spectrum of rotational angles even with shorter sequences, enhancing its adaptability to longer contexts without the need for extensive long-sequence data. Overall, AnchorAttention not only improves long-context performance, but also accelerates the training process, requiring less than 50% of the training time compared to standard attention methods.
How was the effectiveness of AnchorAttention validated or tested in the experiments? What specific datasets and benchmarks were used, and what metrics were adopted for performance evaluation?
The effectiveness of AnchorAttention was validated through experimental results on the long context benchmark ruler, which evaluates the model's ability to handle extensive context lengths. The experiments involved training a 128K model based on the Llama 2-7B architecture, using the SlimPajama dataset, which includes diverse text sources. Additionally, real-world long-context benchmarks like LongBench were utilized to assess in-context learning performance while preserving general task capabilities, measured through metrics such as perplexity, PPL, and performance on the ruler benchmark. The ruler benchmark specifically tests abilities like locating data within vast content and tracing relationships across broad contexts, making it suitable for evaluating long context processing. Overall, the results demonstrated that training with AnchorAttention consistently outperformed other attention mechanisms across various context lengths, confirming its effectiveness.
What specific results were achieved with AnchorAttention in terms of long context benchmarks, and how did it compare with other methods in the study?
AnchorAttention demonstrated significant improvements in long context benchmarks, consistently outperforming full attention, standard intra-document attention, and an improved version of intra-document attention on the ruler benchmark across context lengths from 8K to 128K tokens. Experimental results indicated that AnchorAttention not only enhanced in-context learning performance on real-world long-context benchmarks like LongBench, but also largely preserved the model's capabilities on general tasks such as MMLU and HelloSwag. The method's design, which treats the first token as a shared anchor, effectively mitigated inconsistencies in positional understanding that arose from using BFloat16 precision. This innovation allowed the model to learn the full rotational span from sequences shorter than the maximum context length, thus reducing the dependency on long sequences for training. Overall, AnchorAttention proved to be a powerful solution for improving long context training efficiency and performance.